Hi, I'm Jayaprasad B, Assistant Professor, Government Engineering College, Kerpeta. Today, I will discuss about Module 4 of RC Division of Structural Elements, that is 18 CB 53. The Module 4 is Limited Division of Staircases and Slabs. Slabs. So, we'll discuss about the division of staircases. That is introductory part, introduction. What is staircase? Staircase is an important component of the building, which is the connectivity between the two floors. That means the connection between the two floors in the building. It consists of flights, steps, usually with one or more intermediate landings, maybe in horizontal platform, right between the floors. The horizontal top portion you call it as a straight, and the vertical projection you call it as a step. That is stepwise. You call it as a riser. These two are the very important component in the staircases. The value of the range between the dimension of your thread and rises maybe around 300 mm to 150 mm, ideal for the public buildings. A typical flight steps consists of a two landing and one is going. Generally, rises in a flight should not exceed about 12 in numbers. The step in flight can be designed in a number of ways, with waist slab, with the thread riser arrangement, without waist slab also can do this, or isolated thread slabs. So here we can see this. It's a typical staircase plan and a section. So this is the landing portion. This is the landing portion. These two are the landing portion. So this is the stair parts. So in plan, you can see only threads. Okay, if you come to section, this is the raise part, a stepwise. This is the raise part. This is the raise part. This is the waist slab. This is the landing portion, and this is the landing portion. If you see these two figures, one is plan and another is section, you can understand the concept of stairs. Yes. So types of stairs depend upon the geometrical configurations. So you can classify or you can make the stairs depend upon the geometrical configuration. One is straight stairs with or without intermediate landing. Another one is quarter turn stairs, dog-legged stairs, open well stairs, spiral stairs, and helicoidal stairs. These are the type of the staircase depend upon the geometrical conditions. How it looks. You just see these figures. See these figures. This is a straight staircase. See, these are the rise and threads. These are the steps, and this is the landing portion. Just it is straight. See, quarter turn stairs. Just it's turning here after the landing. Just 1/4 of this length. Quarter turning. So this is dog-legged staircase. This is the landing portion of two flights, right? Seems to be dog-legged. It's look like a dog-legged. Hence, we call it as a dog-legged staircase. Open wall staircase. See, this is the staircase. Landing, steps, landing, and landing staircase. Landing 1 second. This is staircase. So this is the open space. It's just like a well. That's what we call it as an open well staircase. See, spiral stairs. Spiral stairs it is. Circular like this. And then helicoidal stairs. See this geometry. So that's what. Depend upon the geometry, you can choose a type the staircase. I think this is the just a general concept of a staircase. So next we will move to one numerical example, how we are going to design this. Yes. Say numerical example. We take design a waist slab type it is, dog-legged staircase for an office building, given the following data. Say height of floor, that is between the floors is 3.2 meters, rise is 160 mm, that is 270 mm. Width of leg, that is equal to width of landing, it is coming around 1.25 meters. Live load is 5 kN per meter, and floor finished is 0.6 kN per meter. Assume the stair to be supported on 230 mm thick masonry walls at the outer edges of the building, parallel to the rises. That is there in the figure. Use M20 concrete and Fu415 steel. Assume mild exposure conditions. Right. So this is the problem. See, this is the solution. First, you have to write what is given data. Rise is given 60 mm, thread is given 270 mm. So we have to add 22 mm extra for the rise and threads because it's a knock distance, right? So once you add 270 mm plus 22 plus 22, it will coming around 340 mm, 314 mm. So now the effective span, that is equal to center distance between the support, will get 5.16 meters. Everything is there in the figure. I will show that figure. Assume the base slab thickness is, that is L by 20, that is 5.16 meter converted into millimeter, 5160 divided by 20. It's coming around 258, that is round up to 260 mm. We're also assuming the 20 mm clear cover. It's because of mild exposures and 12 mm dia main bars. So therefore effective depth small d, what it is giving, that is capital D is 260 mm minus 20 mm cover minus dia by 2, will get around 234 mm. The slab thickness in the landing portion is, you will take it as a least of very least, that is 200 mm, because the bending moment relatively very low compared to our flights. Yes. Now load calculation. Now load calculation on the projected plan area. That is nothing but your flight areas. So self height of the base slab. Because we have taken the thickness of the base slab is 260 mm, 25 mm is your density of the concrete, multiplied by, see this 314. 314, we add this 270 plus 22 mm to plus 22 mm for the knock distance, divided by, once again, the thread distance, will get 7.56 kilonewton per meter square. Similarly, the self height of these steps. So steps is the dimension, okay? Width is 0.5 0.16 is the rise, and 25 is the density of the concrete. It will come around 2 kilonewton per meter square. And the floor finish, it's given 0.6 kilonewton per meter square. Lie load is also given, that is 5 kilonewton per meter square. The total is 15.16 kilonewton per meter square. So we have to make a factor of this. Therefore, factor load, that is 15.16 into 1.5, will get 22.74 kilonewton per meter square. This is the load, a maximum load, which is coming on the projected area of your plan. That is nothing but the flight area. Next, the loading is coming on the landing portion. The load is coming on the landing portion. So now we will calculate self height of the slab. So thickness is, we are assuming 200 mm, that is 0.2 into 25 is the density of our concrete per meter length or per meter width. It is coming around 5 kilonewton per meter square. And floor finish, of course, it is given 0.6 kilonewton per meter square, and also lie load is 5 kilonewton per meter square for both landing as well as our flights. So therefore, total load is coming around 10.60 kilonewton per meter square. Factored load is 10.60 into 1.5, will get 15.90 kilonewton per meter square. So now we calculated what is the maximum load coming on the stiles and what is the maximum load coming on the landing portion, are already calculated. So this is the analysis. Next, what is the moment? What is the moment? The geometry is given, how the moment is coming. So reactions, I will take 15.90 into, this is the land distance, plus 22.74 into 2.43 divided by 2, will get around 49.3 kilonewton per meter. Maximum moment, of course, it's a mid-span. Ultimate moment will be coming around 69.30 kilonewton per meter length. See, now mu by bd square, that is coming around 1.265 MPa, that is Newton per mm square. We're assuming, of course, it is given FCK is 20 Newton per mm square and Phi is 415 MPa. So area of steel, that is PT by 100, percent of steel, that is called 100 by AST by 100, is coming around 0.38, 1 into 10 raised to minus 2. So this is, so therefore area of steel required. The PT of area multiplied by length per meter length, that is 1000 mm, into effective depth 234 mm, it is coming around 892 mm square. If you are providing a 12 mm dia bars, therefore required spacing is, it's coming around 127 mm. If you are going to provide a 16 mm dia bars, right, the spacing is coming around 225 mm, center to center. So hence it is provided, we will go for a bigger one, 16 mm dia at 220 mm center to center. So now this is the main reinforcement. Now it's come for a distribution. What is the area required for the distribution steel? That is 0.0012 BT. That is coming around 312 mm square per meter length. So by providing a 10 mm dia bars, the spacing is coming around 251 mm. Hence, you can go to provide a 10 mm dia at 250 mm center to center as a distribution bars. Now, if you come to this figure, see this figure. Very neat. This is the plan. This is the plan of the figure. So this is the required distances. What is the flight distance? What is the landing distance? Everything is there. 230 mm, which is on overall edge. It is the wall is there, 230 mm thickness. So this is the bending moment diagram. How it is coming? You just see this. These are all bending moment diagrams. What is the middle it coming? What is the landing portion is coming? Everything is there. By this, analyze will design the reinforcement. So this is the typical reinforcement details of your staircase. See this figure. So if you refer this, the RC details of your staircase as well as how the bending moment is coming. So you have to make a bending moment diagram in this plan itself. That is very easy to understand how you can calculate the bending moment at the landing and bending moment at the stage. I think this is a sufficient figure to understand the concept of a dog-legged staircase. Thank you. Thank you very much. Thank you.